The GE B36-7 produced 3,600 horsepower. That was more than most freight locomotives operating in North America at the time of its introduction. On paper, this machine should have been a workhorse capable of moving enormous tonnage across the continent. Instead, railroad crews learned something frustrating very quickly. They would notch up the throttle, and rather than surging forward with authority, the locomotive would spin. The wheels would break traction, sparks would fly from the rail, and forward momentum would stall. This is the story of a locomotive that had plenty of power but couldn't put it to the ground. The B36-7 discovered a fundamental truth of railroad physics. Horsepower means nothing without adhesion. By the late 1970s, American railroads faced mounting economic pressure. Deregulation was on the horizon, labor costs were climbing, and the solution that seemed most obvious was to move more freight with fewer locomotives and smaller crews. The math appeared. Straightforward. If you could increase the horsepower of individual locomotives, you could reduce the number of units needed to move a given train. Fewer locomotives meant lower fuel consumption per unit, reduced maintenance costs, and smaller crews. General Electric and Electromotive Division were locked in fierce competition for the freight locomotive market. EMD had dominated for decades with their GP and SD series, but GE was gaining ground with the Universal series and then the -7 line. Both manufacturers understood that railroads wanted more power. In 1980, GE introduced the B36-7. The designation told you what you needed to know. The B indicated a BB wheel arrangement with 4 axles. The 36 represented 3,600 horsepower. The 7 placed it in the -7 product family. This represented a significant jump from the B30 to 7, which produced 3,000 horsepower. GE had added 600 horsepower, a 20% increase, using essentially the same platform. The critical detail that would prove problematic: GE did not proportionally increase the locomotive's weight. The B36-7 weighed approximately 280,000 pounds in standard configuration. This was actually lighter than some competing 6-axle designs. The assumption underlying the B36-7's design was that more horsepower automatically translated to more pulling ability. This assumption ignored a fundamental constraint that railroad engineers had understood since the earliest days of steam locomotion. A locomotive can only pull as hard as its wheels can grip the rail. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. The heart of the B36-7 was General Electric's FDL-16 prime mover. This was a proven 16-cylinder diesel engine that GE had been refining for years. For the B36-7 application, GE increased the fuel delivery and adjusted the power curve to extract 3,600 horsepower from the same basic engine architecture. The FDL-16 was not an experimental power plant. It had accumulated millions of miles in service across GE's locomotive fleet. Railroads trusted it for reliability and maintainability. The 6-axle configuration theoretically offered advantages for traction. With 6 wheels in contact with the rail instead of 4, the locomotive's weight was distributed across more contact points. This should have meant lower force per axle and, in theory, better adhesion characteristics. Additionally, the CC truck arrangement, with 3 axles per truck, was standard for heavy freight service. 6-axle locomotives had been the backbone of mainline freight operations since the 1960s. Railroads purchased the B36-7 expecting to accomplish a specific goal, replacing multiple older units with fewer, more powerful locomotives. A single B36-7 producing 3,600 horsepower could theoretically replace older units producing 2,500 or 2,800 horsepower while offering better fuel efficiency and reduced maintenance burden. Southern Pacific, Conrail, and several other major railroads placed orders. The specifications looked excellent. The price was competitive. The delivery schedule met operational needs. On paper, the B36-7 appeared to be exactly what the industry wanted: a modern, powerful, efficient freight locomotive built on proven technology. Here is where the B36-7 ran into physics. The coefficient of adhesion describes how much tractive force a locomotive can apply before its wheels begin to slip on the rail. Under ideal conditions, with clean, dry rail and new wheel treads, a steel wheel on a steel rail achieves an adhesion coefficient of roughly 0.25 to 0.30. This means a locomotive can exert a pulling force equal to about 25 to 30% of its weight on drivers before wheel spin occurs. Under less ideal conditions, this number drops dramatically. Wet rail might reduce adhesion to 0.18 or lower. Leaves, oil, frost, or sand contamination can push it even lower. Grades compound the problem because gravity is now working against you. The B36-7's fundamental problem was a mismatch between its power output and its ability to convert that power into useful tractive effort. At 280,000 pounds, with an adhesion coefficient of 0.25, the B36-7 could theoretically exert about 70,000 pounds of tractive force before wheel spin. This calculation assumes perfect conditions and equal weight distribution across all axles. However, 3,600 horsepower is a tremendous amount of energy to manage. When that power was applied aggressively, especially at low speeds where tractive effort demand is highest, the B36-7 would exceed its adhesion limit almost instantly. The problem was worsened by dynamic axle unloading. As a locomotive accelerates or encounters track irregularities, weight shifts between axles. The suspension system cannot perfectly compensate for these rapid changes. Momentarily individual, axles may carry less weight than their static rating, reducing their adhesion capacity. When an axle becomes even slightly unloaded, it becomes vulnerable to slip. And when one axle slips, the dynamic effects can cascade to adjacent axles. The B36-7 had the power to reach this adhesion ceiling almost immediately when starting a heavy train. The locomotive would spin not because it lacked strength, but because it had more strength than it could apply to the rail. This was not a failure of engineering in the traditional sense. The engine worked, the traction motors worked, the electrical systems worked, but the locomotive had been designed past the physical limits of the wheel-rail interface. General Electric equipped the B36-7 with wheel slip detection and control systems. These systems monitored wheel speed and, when slip was detected, reduced power to regain traction. The theory was sound. If a wheel begins to spin faster than it should, based on locomotive speed, the system detects the discrepancy, reduces power to the affected traction motor, and allows the wheel to regain grip. In practice, the B36-7's wheel slip control exhibited a problematic behavior pattern. When the locomotive applied power and encountered slip, the control system would cut power aggressively. This was protective logic designed to prevent wheel and rail damage. However, the power reduction was often more severe than necessary. Once traction was regained, the system would reapply power. But because the locomotive had so much power available, it would often exceed the adhesion limit again, almost immediately. Slip would recur, power would cut again. The result was an oscillating cycle. Power on, slip, power cut, traction regained, power on, slip. This cycling prevented smooth, continuous acceleration. Crews described the sensation as frustrating. You would notch up the throttle expecting the locomotive to pull, and instead, you would feel this hesitation, this cycling, as the wheel slip system fought against the locomotive's own power output. Experienced engineers learned to feather the throttle, advancing it gradually and watching for the first signs of slip. This technique helped, but it required constant attention and finesse. Under heavy tonnage conditions or poor rail conditions, even skilled throttle work could not prevent the cycling behavior. The comparison to EMD locomotives was telling. EMD's contemporary offerings, particularly the SD42 at 3,000 horsepower, felt stronger to crews despite having less rated power. This was because the SD42 had a better balance between power and weight, and its wheel slip control responded more smoothly. The SD42 might have had 600 fewer horsepower on paper, but crews could use more of its available power more of the time. The B36-7 had impressive specifications that it often could not deliver in actual service. Railroads are practical organizations. When equipment does not perform as expected, they adapt their operations rather than accepting ongoing problems. The B36-7 was not withdrawn from service or returned to the manufacturer. Instead, railroads adjusted how and where they used these locomotives. Assignment patterns changed. The B36-7 was moved away from heavy-grade territory, where high tractive effort at low speed was essential. Mountain grades, helper districts, and drag service over significant elevation changes became less common assignments. Instead, B36-7s were often assigned to run through service on relatively flat territory, where they could develop speed and where momentary wheel slip was less operationally critical. Western railroads found them more useful on desert main lines than on mountain crossings. Consist strategies evolved. Rather than placing B36-7s in the lead position, where their wheel slip behavior would be most noticeable and problematic, railroads often placed them mid-train or as trailing units. In these positions, other locomotives provided the initial starting effort, and the B36-7 contributed once the train was already moving. When B36-7s were used in leading positions, they were often paired with heavier units that could compensate for adhesion limitations. The combination of a heavier locomotive starting the train and the B36-7 providing supplemental power, once moving, worked better than relying on the B36-7 alone. Some railroads experimented with adding ballast to increase weight and improve adhesion. This helped to some degree, but reduced one of the supposed advantages of the design, its favorable power-to-weight ratio. Control logic refinements came over time, but they could not fundamentally solve a problem rooted in the basic power-to-weight relationship. The industry quietly accepted that the B36-7 was not the universal solution it had been marketed as. It had roles where it worked adequately, but it would never be the dominant freight locomotive that its specifications suggested it should be. General Electric built approximately 222 B36-7 locomotives between 1980 and 1985. This was a modest production run compared to genuinely successful designs. The SD-42, for comparison, saw over 3,900 units built. The B36-7 taught the locomotive industry an expensive lesson about the relationship between power and adhesion. Raw horsepower is only valuable if you can transmit it to the rail. A locomotive that produces 3,600 horsepower but can only use 2,800 of it before exceeding adhesion limits is not truly a 3,600 horsepower locomotive in practical terms. GE learned from this experience. The Dash 8 series that followed incorporated heavier frames and improved weight distribution. The C39-8 and C48, for example, were substantially heavier machines that could better utilize their rated power. Wheel slip control technology also advanced significantly. Modern AC traction locomotives use sophisticated computer control systems that can manage individual traction motors with far greater precision than the technology available in 1980. These systems can detect the onset of slip and modulate power in milliseconds, maintaining optimal adhesion continuously. Contemporary locomotives like the GE ES44AC and EMD SD-7ACZ produce well over 4,000 horsepower, but they also weigh significantly more than the B36-7, and their adhesion control systems are generations more advanced. The fundamental physics have not changed. Steel wheels on steel rails still obey the same coefficient of adhesion constraints they always have. What has changed is that locomotive designers now respect these limits from the beginning of the design process rather than discovering them in service. The B36-7 did not fail because it was poorly built. The engine was reliable, the electrical systems worked, the basic structure was sound. It failed because it was designed past the adhesion ceiling. General Electric built a locomotive that had more power than the wheel rail interface could transmit. No amount of throttle skill or operational adaptation could fully overcome this fundamental mismatch. In the end, the B36-7 stands as a reminder that in railroad engineering, the connection between wheel and rail governs everything. You can build the most powerful prime mover in the world, install the most efficient traction motors, and design the most aerodynamic car body. None of it matters if you cannot put the power to the ground. The locomotive that slid instead of pulled taught an industry that weight beats power when adhesion is the limiting factor. That lesson shaped every heavy freight locomotive designed since.